Okay, so let us look at chapter 14, the fundamental theorem of calculus. This is the final chapter that we'll be covering before the final exam. And it starts off by trying to answer the question, why do we care about integration? Okay, theorem 1, the fundamental theorem of calculus 1. Okay, it's called the first fundamental theorem of calculus. I'll be abbreviating it as FTC1. What does it say? Let f be integrable on a to b, and define capital F on a to b by capital F of x is equal to integral from a to x of f of x, of following the notation of the book that we used previously, just integral f. Then what we have is that if f is continuous on at c, continuous at c in AB, then f is differentiable. F is differentiable at c, and f prime of c is equal to small f of c. Okay, with a small note that if c is equal to a or b, take in the first case it would be right, and so right or left hand derivative, So if every other point f prime of c is equal to f of c if f is continuous at c. Note, the function does not need to be continuous from a all the way to the c. It just needs to be continuous at c for this theorem to be true. Okay, so that's my first great and nice theorem, because this is in a way telling me some function whose derivative at c gives me f of c. Okay, so I am going to assume c belongs to a comma b. You can extend this proof to a or b very easily. I'm not going to do that. I'll leave that for you. By definition, f prime of c is equal to limit h goes to 0, f of c plus h minus f of c all the way over h. Right? Now, first, suppose h is greater than 0. We'll consider two cases. H is greater than 0, h is less than 0. Right? Then what do we get? Then c plus h is greater than f of c, and so f of c plus h is minus f of c. Well, this by definition would be integral from c to c plus h of f, right? But what is c to c plus h of f? Well, here's how we do it. Define small m h and capital M h as small m h is equal to infimum f of x on the interval c smaller than or equal to x smaller than or equal to c plus h, and capital M of h is equal to supremum on the same interval f of x c smaller than or equal to x smaller than or equal to c plus h. Great. Therefore, I know from chapter 13 that mh times h is smaller than or equal to integrals from c to c plus h of f. It is smaller than or equal to mh dot h. Okay, and therefore, well, mh is smaller than or equal to f of c plus h minus f of c all the way over h is smaller than or equal to capital M of h, right? Now, exact same thing works out if if capital M is smaller than 0. If similarly, if h is smaller than 0, then look at um, mh comma mh in interval c plus h comma c, right? And again, you would still get that again, you would get that mh times h is this time greater than or equal to f of c plus h minus f of c is greater than or equal to mh times h, and but h is now negative, therefore again small h is smaller than or equal to f of c plus h minus f of c over h smaller than or equal to capital M of h. Okay, so in both cases I get this identity. There's a couple steps that I'm skipping from here to here. Okay, couple steps necessary, but I'm going to assume that you will be able to fill these out. It's exactly the same way as before. Okay, just I'm too lazy to write them, let's be honest. Okay, so it follows exactly the same way that you get this. Okay, my bad, this shouldn't have been from here to here, but instead from here to here. Okay, well, great. So in both cases I do get this. Well, what happens however limit h goes to 0, small m of h is equal to limit h goes to 0, capital M of h is equal to f of c, as f is continuous at c, right? And therefore, by squeeze theorem, therefore, limit h goes to 0, m of h is smaller than or equal to limit h goes to 0, f of c plus h, c plus h minus f of c all the way over h is smaller than or equal to limit h goes to 0, capital M of h. And therefore, I have f of c is equal to limit h goes to 0. Well, I am just going to skip that part. Is equal to f prime at c. Okay, and that is exactly what I wanted to prove initially, and so I have my first result. Okay, an important consequence of this corollary is that if f is continuous on a to b, if f is continuous on a to b, and small f is equal to actually g prime for some function g, for some function g, then I get integral a to b f is actually gb minus ga, right? So what that means, if I actually integrate, if I take the derivative of g, right, and then I integrate it from a to b, the value is going to be g of b minus g of a. How do we prove this? Well, the proof is relatively simple. Let f of x is equal to integral a to b small f, then f prime is equal to f is equal to g prime on A to B. Now be careful. This does not mean that capital F is equal to capital G. However, it means, therefore, there exists some C such that C in R such that F is equal to G plus C. Right? It just means that they differ by a constant. Okay? And what is the C? The number C is equal to, well, I know f(0) is equal to f of a, right? Because it would be the integral from a to a. Well, this is equal to g of a plus c. Therefore, g of a, therefore negative g of a is equal to c. Okay? And therefore, capital F of x is equal to f of x, g of x minus g of a. Right? In particular, integral from a to b is equal to f of b is equal to g of b minus g of a as required. Okay? And so that is what we have. So we'll have some questions. Exercise. Suppose f is integrable. Suppose f integrable on a to b, and capital F of x is equal to integral a to b, a to x of small f. A is smaller than or equal to x, smaller than or equal to b. So I'm on the proper interval. First, does f differentiable at c, does f differentiable at c imply capital F differentiable at c? Okay. Second, does f differentiable at c imply f prime continuous at c, and third, c, maybe I should have called these 1, 2, 3, but well, whatever. Without assumption that f differentiable at c, do we still get f prime continuous at c? Do we still get f prime continuous at c? Answer. So I'm not going to answer all of these. I will just do one, and yeah, I'll just do one. So part A. Suppose A is differentiable at c. Does that mean f prime is differentiable at c? Well, f differentiable at c implies small f is also continuous at c. And therefore, by the fundamental theorem of calculus, by fundamental theorem of calculus 1, I get that capital F is differentiable at c. Okay, let's try to do B also. Does f differentiable at c, small f differentiable at c, imply that f prime is continuous at c? Well, now f prime is going to be exactly small f of x, right? And so if my small f is differentiable at c, I am going to see that, oh, this is going to work if and only if f prime f prime continuous at c. What was I doing? Does f differentiable at c imply f prime continuous at a? Well, f prime is equal to small f, which is differentiable, and so it should be continuous, right? So we want to show limit x goes to c, capital F prime of c is equal to, capital F prime of x is equal to f prime of c, right? If f is continuous at c, if f is continuous, is differentiable at c, if f is differentiable at c, there exists epsilon greater than 0, or maybe a delta greater than 0, maybe delta greater than 0, such that small f is continuous on c minus delta to c plus delta, right? And therefore, f prime, f is differentiable for every x between c minus delta to c plus delta, right? And f prime of x, capital F prime of x, is equal to f of c, f of x, right? Therefore, in this limit x goes to c, f prime of x is equal to small f of c, as f is continuous at c. So yes, we do get that it is continuous. Okay. And a better reason for this we will see soon. Okay, I'm going to leave C as homework. It is actually one of the easiest parts of this. Okay. And thus we get theorem 14.2, whatever, I'll just call it, which is FTC part 2, the second most important theorem. If f is integrable on a to b, and if small f is equal to g prime for some function g, then integral a to b of f is equal to g of b minus g of a. Oops. Proof? Well, this is relatively similar to my fundamental theorem of calculus 1. I am trying to say here that, oh, if f is actually the derivative of such a function of some function f, then I can write integral a to b in terms of the function g, right? And for that, all I need is f to be integrable and it to be a derivative of some function, right? So this is actually a stronger condition than corollary in a way, right? I'm saying that f is integrable rather than continuous, and it is the derivative. Okay, so let us try to show that this actually holds true. So let p is equal to t0 to tn be any partition, of, oops, terrible brackets, a to b, then by mean value theorem, there exists a point, there exists xi in ti minus 1 comma ti such that g of ti minus g of ti minus 1 is actually equal to g prime of x ti minus ti minus 1, which is, well, because g f prime x is equal to g prime x is equal to f of x, this is exactly equal to f of x times ti minus ti minus 1. Great. Well, if I again define if mi is equal to infimum f of x on the interval ti minus 1 smaller than or equal to x smaller than or equal to ti, and capital Mi is equal to supremum on the same interval f of x such that ti minus 1 smaller than or equal to x smaller than or equal to ti, then what do we get? Where did I go? Right. Then it is clear, then clearly, well, if f of x, if I am having this as the maximum and minimum values of f of x in this interval, clearly small mi times ti minus ti minus 1 is smaller than or equal to f of x times ti minus ti minus 1 smaller than or equal to capital Mi times ti minus ti minus 1. Right, so I might have misspoken slightly initially. I don't remember if I accidentally said it otherwise, but fundamental theorem of calculus is a stronger statement of the corollary, because if f is continuous on a to b, it is integrable on a to b. We have seen that before. But integrable on a to b does not mean it has to be continuous, right? Integrable just means that the lower sum has to equal to the upper sum. And so we want to show that, oh, if that happens, life is good, right? Therefore, mi times ti minus ti minus 1 is smaller than or equal to g of ti minus g of ti minus 1, smaller than or equal to capital Mi ti minus ti minus 1. Well, adding these all up, therefore, summation I is equal to 1 to n mi ti minus ti minus 1 is smaller than or equal to, well, if I add all of these up, this more or less forms a telescoping sum, right? All of them cancel other than GA and GB, which leaves with I is equal to 1 to n capital Mi ti minus ti minus 1. Great. Did I mention a partition? Oh yeah, I didn't mention that P is a partition. Therefore, LFP is smaller than or equal to G of P minus G of A is smaller than or equal to U of FP for every partition A. For every partition P. But well, I assumed that my function f is integrable. Therefore, as f is integrable, these both limit of capital L FP is same as limit. The infimum of U FP is same as the supremum of L FP is equal to the integral, and therefore by more or less this equivalent of squeeze theorem, not exactly squeeze theorem, but equivalent of squeeze theorem, I get that this is equal to capital F. Yay! We have shown the second fundamental theorem of calculus, and we have found our integral. Okay? What? Oops. My bad. And why can't I? 100%. Okay. That should work. Okay, let's do some related exercises. Exercise. First, consider the function f of x is equal to, from 0 to 1, it is 1 between 0 and 1, and 0 from 1 to 2. 1 strictly smaller than x, smaller than or equal to 2. Great. A. What is capital F of x is equal to 0 to x f of t dt on 0, 2. Okay, so now there's a small thing that has happened. We are now more or less referring to my function. This is the same as integral a to x f. Okay, but we are going to try and follow the conventional notation and write it as integral f of x dx. Okay, we didn't write it so far, but from now on we will be writing it this way. It is important oftentimes whether what my variable is, right? If my variable is not the same as this top variable x, things could go very wrong. So it is important to know which variable I am doing stuff with. Okay, so whenever I'm writing a to x f, that generally means a to x f of t dt. Okay, so first what is f of x? Second, is f of x continuous? And part 3, c, is f prime of x is equal to small f of x forever. Under what conditions? Okay. I don't think I'm going to do any of these. I am going to leave these as homework for you guys to work through. Okay. For now, I might do some problems later. On Thursday, for a video on Thursday, so that you have some questions that you can more or less reference before the exam. But for now, I'm going to leave these as homework for you to work on, just so that you have some questions to look at from this chapter. exercise. Suppose f differentiable and differentiable f of 0 is equal to 0. 0 is smaller than f prime is smaller than or equal to 1. Okay, so my function is strictly positive. Okay, then, but it's also smaller than 1 for every x. Then, for every x greater than or equal to 0, show integral 0 to x f cube is smaller than or equal to integral 0 to x f whole squared. Okay, so first of all, let me just clarify these notations again. This is integral 0 to x f cube of t dt, and this is integral 0 to x f of t dt, all of that squared. Okay, all yeah, I'll again leave these for homework. I'll see if by Thursday people are unable to do these, or Friday, I'll try to post solutions to these, and so that you can more or less have some idea of how to do these. But I don't think these are too hard of questions to work on with. Okay, another exercise. Chain rule for integrals. Chain rule for integrals. Now this is something that is slightly important. Okay, actually this is very important. So suppose h continuous f comma g differentiable and capital H of x is equal to integral small f of x to small g of x of h of t dt. Okay, so far we have seen my integrals from 0 to x, 0 to something, or a constant a to x, a to b. This time I have both of these as functions of f of x. None of these is x, none of these is a constant, possibly. Even if they are, life would be fine. How do we work with this? Well, then capital H prime of x is actually h of g of x times g prime of x minus h of f of x times f prime of x. Okay, you want to show this? I am not going to do the full proof. Okay, since I'm going to write this again, I'm going to give this as a homework again, but I'll give you a hint. Reduce to the cases, or actually, I'll give you a better hint. Suppose C belongs to the interval f of x to g of x. Then integral f of x to g of x h of t dt is equal to integral f of x to c h of t dt, c h of t dt, plus integral from c to g of x h of t dt, right? And while this is not the complete proof, the further idea is, oh, now do I have this? How do I use chain rule? use chain rule for derivatives by taking u of x is equal to well, let me just say chain rule of derivatives, which says, hey, d over dx of, let me say, u of x is equal to d over dx of f of x multiplied by d over dx d f of x of u of x. Okay, that's the chain rule for derivatives. If you use that properly, this should be really easy, right? Yeah, that's my big hint. You have to be slightly careful because the way chain rule works, way integration works is you have to substitute the top number in terms of in place of t when you do fundamental theorem of calculus 1 or 2. It gets replaced by the top number, so you have to be careful whether you're putting g of x or h of x or what. Okay, how do you put that? Okay, let me give you one more problem to think about. Exercise: show that the value of functions, the values of this expression do not depend on x. Capital F of x is equal to integral 0 to x 1 over 1 plus t squared dt plus integral 0 to 1 over x 1 over 1 plus t squared dt. Okay, now the thing is, you'll have to systematically prove this. Okay, but I'll give you a hint for this one also. Hint: if you you should use the previous use chain rule as we do not know arc tan of x. Okay, so you will have to use the chain rule rather than saying, oh, I know the integral, I know that the integral of this is exactly arc tan of x, and trying to cheat with it. No, that doesn't work. You'll have to do it in a better fashion. Okay, and then let us finish off the chapter with the final theorem. Theorem 14.3, which says, oh, if suppose, well, I can just call it theorem 3. I don't need to write it 14.3, whatever. Theorem 3. Suppose f continuous on a to b, then f is integrable. Then f is integrable on capital A to capital B. Okay. Proof. So first of all, this might seem, hey, slightly similar. You might oops, you might think, oh, can I use anything? This sounds similar to stuff in chapter 13, which said that, oh, if I have certain conditions, then f is integrable. But we never actually showed that if it is continuous, then the partitions are equal, right? So now we want to show that, oh, if the function is continuous, then I can then I can show that it is actually integrable, and so I don't need to worry too much about what kind showing partitions. Most of my functions will be integrable. In fact, you don't actually need it to be continuous on a to b. If f is continuous, no, actually you do need, my bad. Okay, so define L and U on AB by L of x is equal to L integral a to x small f, and U of x is equal to U integral a to x of f. Okay. Well, what are L and U? Well, where L is L integral a to b is equal to infimum supremum L f comma p, and U f comma p, sorry, L a to x, sorry, there should be f a to x f is equal to infimum U f comma p. And why am I defining it this way? Why am I not calling just them integral? Because I do not know if the function is integrable. I'm just calling these as the supremum and infimum of these sets. Okay, great. They need not be equal. I do not know that the function is integrable. If the function is integrable at x, right? Then then Lx is going to be ux, right? If the function is integrable from a all the way to b, then Lx is equal to ux everywhere on a to b. Okay. So let x belong to a to b, Okay. If h is greater than 0, and I'm going to define small h is equal to infimum f of t, where x is smaller than or equal to t, smaller than or equal to x plus h, capital M of h is equal to supremum f of x, x smaller than or equal to t, smaller than or equal to x plus h. Once again, I'm going to say that if x is smaller than or equal to 0, precisely the same argument is going to happen. Then we have shown this similarly before. Well, this is smaller than or equal to L x to x plus h. Well, I know that this is going to be smaller than U x to x plus h. F smaller than or equal to capital M of h. I do not know if the middle two terms are equal, but I know this is true. So small m h is smaller than or equal to L of x plus h minus L of x, smaller than or equal to U of x plus h minus U of x, smaller than or equal to mh times h. Okay. Okay, and therefore mh is smaller than or equal to L of x plus h minus L of x over h smaller than or equal to U of x plus h minus U of x all over h is smaller than or equal to m of h. Sorry, that should have been an h here. Similarly for h smaller than 0, and therefore by argument as before, limit h goes to 0, m of h is equal to limit h goes to 0, capital M of h, we get that is equal to f of x, actually, not c, sorry, my bad, f of x. I get that, therefore L prime of x is equal to U prime of x is equal to small f of x. Okay, great. I have shown that the derivatives are equal. Once again, this creates a problem. This does not mean they're equal. Therefore, there exists a C in R such that U of x is equal to L of x plus C. That is all I can say for every x in a to b. Okay, that is all I can say. I can't say that this function is they are equal, but I can say they differ by a constant everywhere, and that is the key. They have to differ by the same constant everywhere. Since U of a is equal to L of a, C is equal to 0. Therefore, U of x is equal to L of x for every x in a to b, right? Because what is U of a? It is the integral from 0 to a to a, which is 0. What is L of a? It is the integral from a to a, which is 0. And therefore, U of x is equal to L of x. Therefore, U a to x f is equal to U of b minus, which is equal to L of b is equal to L integral from a to b f. And this means that f is integrable. This means f is integrable on a to b as we required. Okay, and I'm going to stop this part here. This is going to be the final chapter that we have on the exam. I'll try to upload some worked out examples for this and chapter 13 that you guys struggled with by Thursday, so that you have some idea about problems on the exam. Okay, let me know.